Drop a solid piece of steel into water, and it sinks almost immediately. Yet an enormous ship built from thousands of tons of steel can cross an ocean without disappearing beneath the surface. The explanation is not that steel somehow becomes lighter. The answer lies in the ship's shape, the air trapped inside its hull, and a physical principle discovered more than 2,000 years ago. For centuries, ships were mainly built from wood. Wood naturally floats, so early shipbuilders did not need to understand advanced physics. But wooden vessels had serious limitations. They could rot, burn, break apart in powerful waves, and required enormous quantities of timber. As ships became larger, engineers began searching for a stronger material. Iron appeared to be the obvious solution, except for one problem. Iron sinks. In 1787, English industrialist John Wilkinson challenged that assumption by constructing a flat-bottomed iron barge. Many observers expected it to fall straight to the bottom of the River Severn. Instead, it settled into the water exactly as Wilkinson had calculated and floated successfully. Several decades later, engineer Isambard Kingdom Brunel proved that metal ships could survive far more than calm river journeys. His vessel, the Great Britain, was launched in 1843. At almost 100 meters long, it was one of the largest engineering projects of its time and the first major iron ship designed for regular Atlantic travel using a propeller. Critics predicted disaster, but the ship crossed the ocean successfully. It later ran aground near Ireland and remained exposed to waves for months. A wooden vessel might have broken apart, but its iron structure survived and was eventually recovered. From that point forward, metal became the future of shipbuilding. The reason these vessels floated can be explained by Archimedes' principle. When an object enters water, it pushes some of that water out of the way. The water then produces an upward force equal to the weight of the displaced liquid. A flat steel plate displaces only a small amount of water and has almost no air inside it, so it sinks. Shape that same plate into a wide bowl, and it pushes aside a much larger volume of water. The bowl also contains air, reducing the average density of the entire structure. A ship works in exactly the same way. Its hull is not a solid block of steel. It is a huge hollow structure containing machinery, cargo, compartments and large volumes of air. Although the steel itself is denser than water, the average density of the complete ship remains low enough for the displaced water to support it. As weight is added, the ship settles deeper. It continues descending until it displaces enough water to create an upward force equal to its total weight. This is why heavily loaded vessels sit lower in the ocean than empty ones. Modern ships can also adjust their position using ballast tanks. An empty cargo ship may sit too high, making it unstable in rough seas. To lower its center of gravity, seawater is pumped into special tanks inside the hull. The additional weight makes the ship sit deeper and improves stability. When cargo is loaded, much of that ballast water is removed. Otherwise, the combined weight could push the vessel dangerously low. Crews carefully calculate cargo distribution, ballast levels and draft before departure. Submarines use the same principle in a more dramatic way. To dive, they allow seawater into their ballast tanks, increasing their average density. To rise, compressed air forces that water back out, making the submarine less dense than the surrounding sea. This principle can support structures of astonishing size. The supertanker commonly known as Knock Nevis stretched approximately 458 meters, and when fully loaded, displaced more than 600,000 tons. Its hull extended around 24 meters beneath the surface, yet the water it displaced produced enough buoyancy to keep the entire structure afloat. Large military vessels rely on the same law. A modern aircraft carrier can carry thousands of sailors, aircraft, fuel, ammunition and equipment. Nuclear reactors may provide propulsion, but buoyancy still comes from the volume of water displaced by the hull. However, flotation only works while the hull keeps enough water outside. The Titanic was divided into watertight compartments and was designed to remain afloat after several were flooded. When it struck an iceberg in April 1912, the collision damaged more compartments than its designers had planned for. As water entered the forward sections, the bow sank lower. Water then spilled into additional areas, steadily increasing the ship's average density. Eventually, the upward force could no longer support the flooded vessel. The extreme angle also placed enormous stress on the hull, contributing to its structural failure. The disaster led to stronger international safety rules and improvements in watertight compartment design. Another danger appeared during the sinking of the ferry Estonia in 1994. After its bow structure failed in heavy seas, water entered the open vehicle deck. Because the water could move freely from side to side, it shifted whenever the ship tilted. This free surface effect made each roll worse. Water moved toward the lower side, increasing the imbalance until the ferry capsized. The physics had not failed. The vessel had simply moved beyond the conditions its design could safely manage. So how large could a ship become? From a buoyancy perspective, there is no simple maximum. A kilometer-long vessel could theoretically float as long as its average density remained below that of seawater. The real restrictions come from structural strength, maneuverability, infrastructure and cost. Long ships bend as waves move underneath them. At one moment, the bow and stern may be supported while the center hangs over a trough. Moments later, the center rises on a wave while the ends lose support. Repeating this cycle thousands of times creates fatigue in the hull. Extreme size also makes steering and stopping difficult. The largest tankers may require several kilometers to turn and many kilometers to stop. They cannot safely enter ports without assistance from tugboats. Canals, bridges, docks and water depth impose further limits. A ship may be physically capable of floating but still be unable to reach most ports or pass through important trade routes. For this reason, the largest modern vessels generally remain near 400 meters long. Floating industrial facilities can be even larger because they remain offshore for years instead of regularly entering ports. Ultimately, a steel ship floats because it is not simply a mass of metal. It is a carefully engineered volume filled mostly with air and useful space. Its shape forces the ocean to move aside, and the displaced water pushes upward with enough force to support the vessel. The materials, engines and dimensions have changed enormously throughout history, but the principle remains the same. Every container ship, tanker, ferry and aircraft carrier stays above the ocean because of one simple relationship between weight, volume and displaced water.